So for about the last 15 years, I've been working on creating specs of microprocessors. For a while I was at ARM, building kind of ARM's kind of official kind of formal specification and using it to verify ARM hardware against that spec, and it's publicly available. And now I'm at Intel doing the same thing, but for the Intel architecture, which the rest of the world calls x86, but officially it's Intel architecture. So the big challenges in building a spec of a large specification are not actually, at least for ISAs, it's not actually the technical ones. When Dijkstra wrote what he did back in '76, there was a great specification language for describing kind of processor architectures, and people were using it in compilers and things like that. And then unfortunately everybody forgot about it for the next 20 odd years. But you know, the technical problems are not the biggest challenge. I mean, there are technical problems that we still don't know how to solve, and you know, help with those would be appreciated. But that's not actually what makes this hard. It's fairly expensive to build a large specification of like 50, 100,000 lines of spec. So it involves quite a lot of people. You've also got to kind of change how you do things, whether you're kind of like merely a consumer and you're, say, verifying a compiler. If you already have some way of verifying that compiler, you've got to make changes to it. That's a cost. If you're inside a company, you have a database that's being used within one team, and you want to instead have a central database that's used across all teams in the company, the change to using that is a cost, plus the change of improving that specification so it really can be used by everyone. So there's quite a lot of costs involved, and so and also there's lots of different teams. You know, within a company, there are lots of teams, you know, designing hardware, verifying hardware, testing hardware, writing firmware, writing simulators, writing libraries, compiler support, testing all of that software. There's lots and lots of teams. And then outside, you've got all the people who could use your specification. You know, compiler people, people writing binary lifters, working security stuff, people who want to verify their simulators against the spec. There's lots of people. And if you're going to kind of really be successful, you've got to persuade people to contribute into this whole specification. And then you've got to worry about, well, how are they going to see a benefit? When will they see any benefit, or is it all cost? In which case, they're probably not going to do much to help you. So you've got to think about all these different teams, and those really are the big challenges, more than the technical ones, because a lot, not all, but a lot were solved actually in the early '70s. So the main trick that I've found to make this work, especially kind of like inside companies, which are, you know, have a different dynamic to them, is to find a way of having, you know, a single specification, single set of tools, but then supporting many different teams. And what you really want to do, so, you know, teams like people who are producing documentation, that is super important. At least half the use of a spec is just as documentation, people reading it. But also people verifying and testing against the spec, people extending the spec, designing new instructions, new security features to add to the architecture, people building tools, generating code from the spec, all those different teams. You want that whenever one of them does something which makes the spec or the tools a little bit better, you want that to be helping everybody else. So that you kind of, you know, the spec and the tools are just gradually getting better and better, and you're able to support more teams and get more value out of it. And if you don't manage to set something like this up, it will kind of, you know, just kind of all fall apart. When I joined Intel, I went looking for what had been the previous efforts inside the company, and I think there's 5 or 6 previous attempts at creating formal specs of the Intel architecture. And within ARM, I know there had been at least one previous attempt at building a formal spec. And technically it was actually, I think, better, but socially it didn't quite work. So, what do you want to use this spec for? You kind of like, as you're figuring out your uses and your design goals, you've got to figure out what you want to do with it. So you want to verify basically all the things that are associated with building the processor and using it. Right? So kind of there's software and tools like compilers and binary lifters and so on. You might want to verify those, simulators, firmware, hardware, and so on. But most people aren't doing formal verification. Most are doing testing, so you want to support that. You have to have really good quality documentation. Actually, I think I said most of this in the previous slide. So, but basically, there's a lot of different people doing different things with the spec, and you want to kind of like look for how can you build something that supports most of those. And one of the important things about the spec is it's not all that useful unless it's actually accurate. Right? You can do a little bit with an inaccurate spec. Many people do, but if you want to support many uses, it has to be really accurate. So there's a bunch of things you do to try to make it, to find problems. So while you're building the spec, we do various static analyses. So there's quite a strict type system in the specs that I build. There's model checking can be quite effective. And there's also when we spot kind of unsafe patterns in the spec and kind of like, okay, we spot one bug. Sometimes we write custom checkers to look for issues associated with that. Things involving exceptions are especially unsafe or likely to fail, and so we have a checker that checks things around exceptions. Inside a processor company, at least any processor company that has survived for any length of time has unbelievably good and large test suites, because if they didn't, they've gone out of business. Right? So you have this kind of 50,000, 100,000. I'm not actually sure how many test suites or tests there are inside kind of Intel, but there's an awful lot of them, and so we have lots of these. We can use this as a resource, and basically, you use that by kind of comparing against some reference. Basically execute one instruction, compare what happened. Execute another instruction, compare what happened. So you're kind of like really trying to kind of find every single kind of error as quickly as possible. And then, of course, we do review and so on. And then the other thing is, as you use the spec in various ways, you're going to find other bugs, because you won't match some simulator and you go, okay, who's wrong here? And eventually you figure it out, and sometimes that will be bugs in the spec. And formal verification is especially effective, although what I found was that it's a great way of wasting an engineer's time, is to send them chasing down a hardware bug which turns out to be a spec bug. So you really, really do not want to have too many that turn out to be my fault and not, a problem in the hardware, or you just lose all credibility. Okay, so trying to make this a bit more concrete now, what's actually in the ISA specification? So there's lots and lots of encodings and instructions. There's many different kind of modes, different privilege levels and security features. There's memory, you've got segmentation, virtual memory, and kind of extended page tables, things like that. Exceptions, security features, an unbelievably large number of registers. I mean, you might think there were 32 registers in your processor. You're not even close. And and kind of things to test how many of those features are actually available in the processor, and more still. And the specs are pretty huge. So the ARM spec, and this is kind of largely from memory and anecdote because it's much larger than when I left ARM, but there's certainly over 1,700 instructions or encodings, 1,000 to 2,000 registers, something like that.
It's about 400,000 now.
Well, the lines of spec, there's handwritten spec, about 50,000, and there's maybe it is 400,000 machine-generated lines of code of spec, yeah. But they're generated from other databases, so it's like, you know, the database is really the spec. I mean, it doesn't help you if you're the one trying to model check the generated code, but okay. x86 is a bit bigger. There's a terrifying number of different encodings, but you know, it's maybe twice as big. I think it's not as much bigger as you might imagine, but it is bigger. And something that I was doing kind of like sort of by accident, just a convenient way of doing things, and then I realized it was actually a really important thing, was thinking about what's the structured content, stuff that fits nicely into table format or databases, so things like instruction formats, register fields, things like that, and what is kind of like less structured, things where you really need code. So I could have labeled those data and code. So that structured content is the best kind of content because it's super easy to get people to write. It's super easy to build tools to use it. You know, people can throw together a Python script that reads a JSON file and dumps out a C header file. And if they want a different C header file, they can modify it themselves, and they need virtually no help from me. And so that is, doesn't need much help from me. So that's always a good thing because I've got plenty to do. But people can use this for themselves. So that is the preferred form. But unfortunately, there is this awkward stuff like what does an instruction actually do, and fiddly bits about what the register fields mean and things like that. And this is more kind of squirrely, harder to kind of like capture. So you write code for that. And you might even be writing in multiple languages. So you might kind of like have one language you use for the more deterministic parts of the architecture, and then do something else for the less deterministic bits, like say memory consistency models. And one of the reasons this is such a pain to work with is that generally you have to translate it into some other language before you can use it, because people want SMT, Isabelle, Hall, C++, Verilog, and in fact all of those. You need to be able to generate all of those different languages, and compilers are. It takes a while to understand a compiler well enough that you can modify it, right? So it becomes a bit of a specialized skill working on it. And so, inevitably, they need help from some kind of support team. It's harder to customize. It's just harder to use. So what I've learned is I really want to minimize this. Now, going back to the previous slide, I still expect there will be 100 to 200,000 lines of, about 100,000 lines of handwritten code. So it's not like I'm going to have a small amount of this unstructured content, but I'm trying to minimize it as much as possible. So this is kind of the main thing I've learned over the 15 years is, really strive to get it as much into kind of databases as I can. But even there, that's hard because it turns out that any... Warren?
So you said unstructured. Can you differentiate that in some sense? I'm just trying to understand what you mean by that.
Stuff that's really has to be code, and yeah, code and data are kind of like, can be interchanged, but if I've got a database with a fairly regular structure, and I then find, there's so I've got a whole load of registers, and then I go, but only some of them are read-writable. can be written and some can't. So I add an extra field to it to handle that. And then I find there's something about initialization that is different in some, and I add an extra field. And after a while, I find I'm adding an extra field to my database to handle 2 registers. And then it's probably a bit not really worth adding that extra thing, or the property that's being checked is just too fiddly and awkward to fit in a database. It's a fuzzy boundary. And what kind of you tend to get to is you've got a database capturing almost everything, and there's a few exceptions where you really actually need to write some code, because there's some register that's almost never used, that's only accessible under an extremely obscure and complex condition or something like that. And it's just not worth having a database entry for kind of, the boot time only property, or the kind of like, something like that. So you end up saying, I just have to have a bit of code for this. And so the thing is, you might be tempted when you find your database cannot completely capture everything as just simple data. You might be tempted to go, I won't even bother, I'll write it all as code. And the answer is, that is a mistake. Really work hard to get as much into your database as you can, and then find some way of dealing with the exceptions. So just to give you kind of a more concrete example of some structured data, Intel has released for some years a database of all instruction encodings. And so, it's got some kind of table, a number of fields with the name and the encoding. In x86, the encoding is quite amusing because you describe it with something like resembling an attribute grammar. So, that's a bit more exciting than on RISC architectures. But, that's the kind of thing I'm talking about. And then, as we're describing an instruction, we gather information from multiple kind of places. So we have some additional information we're writing about each instruction. So let me see how much of that is readable. So we've got kind of like things have different categories. So some of it's for documentation. We've got kind of unsigned integer addition of two operands with carry flag. We've got a list of the inputs and their types. We've got information about the encodings. We've got information about the intrinsics. So we build up databases like this, basically trying to kind of capture as much as we can, so that if someone wants to try writing a Python script to do something useful with it, they can do it. And this is actually something that's generated from not Python, but some JavaScript. It's a little website that describes kind of all the instructions we've got specifications for. And kind of if you were to click on, so it's got, you can see most of that information is coming, in fact, all that information from instructions down is coming straight from the database. So we're kind of trying to have that kind of level of documentation information. If I were to click on something, I get a bit more. This shows a list of encodings, again, from that Z database. At the bottom, there's the compiler intrinsics you could use to generate this instruction. There's a little bit, the warning, testing is incomplete, not reviewed by architects. We've got some metadata tracking what's the status of this bit of the spec. Is it good enough yet? This is actually an old slide. It's in better shape than that suggests these days. And then finally, in the middle, there's 2 lines of actual code, which are the spec of this instruction. And this uses a helper function. So we've got kind of, you can click on it and get kind of, here's the helper function. And the thing that makes this an executable spec is you can kind of keep on clicking all the way down until you get down to the kind of the primitive, kind of a small set of primitive operations that make up this specification language. Yeah?
Is this pre-existing, or is this the result of your work?
This is the result of my work, yeah.
It's confidential about it.
It's not really confidential anymore. It's just that we haven't publicly released it yet. So, yeah. And more stuff from the database, but from that database, we're machine generating something which says there's a field called CF that is 1 bit wide, position 0, has a reset value of 0, and can be written to. So, you know, this is serving multiple purposes. Okay, so now the reason this is hopefully interesting to you is we're planning to publicly release this, and we're going to do this as a series of increments, and that's partly because we haven't finished yet, but mostly because what we'd like is feedback on, is this spec actually usable? You know, kind of what would make it easier to use, what would make the tools easier to use. And if we wait until we're all done before we show it to anyone, we're not going to feel like changing things. So hopefully we will still feel like changing things when you make good suggestions on how to make things better. And because we'll be changing things, it will start off not very stable, and we're not finished testing it either, so also not very trustworthy. That will gradually kind of increase. You know, you can't run some tests until you have certain instructions in the, even if they're not the instruction you want to test. So, you know, we can't run all the tests at the moment, and we're gradually increasing that as we expand the spec and debug the spec as well. The plan is some kind of liberal license. I'm waiting for the lawyers to tell me what that actually looks like. We'll have tools. That website I showed you is a demo. So to give you a sense of what's in the first release, it can run factorial, iteratively, and recursively, and compare the results. So it's, you know, like 50 to 100 instructions. I mean, you know, if we have the add instruction, we're going to throw in the subtract instruction because it's almost the same, right? So it's 50 to 100 instructions in that first release, and an awful lot of stuff about how to read operands and write operands and segments and stuff like that. And we'll have a blog as well going along with it, basically, so we, you know, if people are asking the same questions, we can answer them there, and announcements and things like that. We're writing this in the same language that ARM uses, and the idea there is, I mean, the disappointing thing when I persuaded ARM to publicly release their spec is not a lot of people used it, right? And so, you know, my belief is that that's because it wasn't useful enough to invest the effort in figuring out how to use that spec. So, you know, by having ARM and Intel both use the same language, we're hoping that will change and that we will actually be able to kind of get academics using it, but also kind of like random open source projects. Peter?
I want to tell the audience that this whole thing is supposed to be kind of interactive. Give them a tiny example of how to do it. But each of them to ask the commonality of the language is fine and good, and we appreciate it. It adds out to other things. But what about the commonality of this database format?
I think that's custom. I mean, you know, it's going to be similar, but to some degree, probably yes, because there are differences between the ARM and Intel architecture. Yeah, I don't know. Maybe I could. I'm actually due to talk to ARM again, so maybe I could talk about whether we could use the same, except I hate the data formats that ARM uses, having used them for a long time at ARM. And although it might be that they are actually the best choice, and it was just kind of like, you know, you need to think about the full set of uses to really appreciate why they are the way they are.
Common with RISC-V?
Yeah. Does RISC-V have data formats? Okay, we should talk. Okay, so yeah, first release will be small. It will be pretty soon, except I'm going, and by soon I mean me going on holiday tomorrow or next week is a problem. And there's another question.
Okay, it's
a very open-ended and vague question. One of the reasons I'm speculating it's hard to get outsiders to use the spec is that maybe this is sort of, it's a misguided question that's too influenced by your slide earlier, is that the spec very much focuses on aspects of the, of the ISA that are important to other people inside Intel or ARM, but maybe less relevant to, say, imagine I'm a security researcher and I just want to figure out what sort of abstractions about the ISA do I need to think about in order to build, mumble security mechanism, right? And it's almost like that spec is an abstraction of, or is a view of the spec that you are exposing, which has a lot of detail. And so there's a bit of a gap there. I don't know if you saw any of this or you can comment on that.
Yeah, yeah, I mean, there definitely is that, and that's, kind of like some of the feedback we're wanting to get. One thing that I learned talking to, there's a team in Australia, Kate Lamb and Nick something, who've written a kind of partial evaluator or for ASL, and they were, and especially kind of thinking about doing binary lifting of ARM instructions into something that into kind of like convenient SMT for their use. And one thing they said was really hard was for vector instructions. When they generate SMT for it, there's this giant loop that they end up unrolling because of the nature of the SMT they're generating, and after having unrolled it, they have this enormous thing that is really unwieldy because it has 16 replicas of whatever was inside the loop, and they said, could we package up the bit of the thing inside the loop, the kind of scalar operation that's being replicated n times? Could that be extracted and made conveniently available? And so, I'm trying to kind of structure things so that we will be able to generate that. And so, but that's just like one example from one interaction I had. And so, yeah, this is what we want to learn. The early release will not have much about the kind of stuff you want as an OS researcher or a security researcher. It will just be kind of like plain instructions, and so we really want to know kind of like what do you need, and sometimes some things are super easy for a tool to produce, like what's the complete list of exceptions that could be generated from this instruction? What's the footprint of, what registers it's use, what code does it execute? That's super easy to extract. So, knowing what people want, we can throw stuff into tools pretty easily. Another thing is kind of like, we have an idea of what the second release will have in it, and maybe and we're trying to firm up what the third release will have in it. But we really want to know do you want to know the latest instructions, which aren't even in silicon yet, but will be next year and have been kind of publicly announced perhaps, and you've seen them and you wonder, could I have a good spec of those? Because nothing supports those yet, so that'd be great to have a spec for. Or do you want the old legacy instructions, because any binary you look at is using all these instructions designed in the 70s and 80s, and they're the ones which are most useful to you? Or do you want not instructions at all, but OS stuff? So again, if people tell us what they'd like us to focus on, we'll see what we can do about that. Okay, so just wrapping up. So the big changes are kind of really these kind of social things and cost-related things of trying to make sure people are getting value from the spec. Definitely technical issues still to be solved, but that's not certainly not where I get to spend most of my time. And it has to be validated really well to be useful. Supporting many different uses is critical. You want to design that in from the beginning. So we have all that metadata that we use to produce documentation and things like that. Use structured data formats, and we're releasing it soon using this using this ASL language that originally developed at ARM, and now we're using it too. Questions?
Fantastic talk, thanks. Do you get any pushback from the powers that be at Intel for doing this, because it might give a competitive advantage to your other companies?
There's definitely been a discussion with, I think it was the lawyers raised the question of kind of like, how much would I be publishing that isn't already publicly available? And you know, for a large part of it, it doesn't matter, because if you're a company that's successfully making processors that are compatible with our stuff, you've already built your test suites. You've already built any formal validation suite you're going to have, right? So most of it doesn't matter. And generally, for new bits of architecture, we've got the message that clear documentation is actually important for people to be able to use it, especially if it's like a security feature. I remember people telling me that they couldn't use security features and processors without having a spec that they, was clear enough and that they trusted actually matched the hardware. So, if we want our customers to use something, we need clear descriptions. So there's a bit of pushback, but it's kind of okay. Behind Sandham, sorry.
I guess this is sort of the same question in a way. Like, what's the business case for Intel doing this? Like, so having a specification costs them something, which is, firstly they have to like stick to the specification, and then secondly, it's kind of like it costs something to maintain it and like conform all your processes. So like, is this like, why do this? Is it like one thing it might be is it helps your engineers get the CPU right, and actually then releasing the spec is a totally sort of side effect of that. Or another thing is this is a way of communicating with customers, and like this engineers using it is kind of a side effect. So if you're pitching this to your CTO, what's like the reason for doing this?
I mean, you've basically answered your own question there. So it is exactly kind of, customers have been asking for it. It helps customers use stuff. If you add something new to the architecture, and it takes longer for this for someone to build the software that uses it, well, people aren't getting much value out of your latest product. They might as well stick with the old one if there's no software that uses the new features. So you want to enable kind of software teams to be able to kind of use that new feature so people get the value of it. So that's kind of one thing. And then, as you say, kind of internally, it's useful because, I mean, one thing that happens internally is you've got, you write a spec of a new instruction, it gets kind of approved as yes, we're going to actually kind of like add that to the architecture. Now that spec goes to simulator teams writing libraries, compilers, OS support, firmware. It goes to hardware teams, verification teams, etc. And then often what happens is hardware team looks at it and goes, can you make a small change to it? And so the spec gets changed, and and things proceed for another couple of years. And now finally you have silicon back, or you have some, basically once you've got silicon, you're in a position where you can actually try all that software, compiler, libraries, etc. You can try it on silicon. You can only do a limited amount in simulation before you have silicon. So once you get silicon, you find that not everybody noticed the change in the spec. Not everybody was informed of it. Whatever. There's some miscommunication has happened. So it's now like, well, how long will it take us to take the team that has moved on from writing the simulator? They did that work 2 years ago. They're busy doing something else. Stop that, messing up their schedule. Come back, fix the thing, taking weeks, months. Now the software can be fixed. Now you have a product you can actually sell. And you don't know how long that will take, so you don't know how many issues like that you'll have. And that's on top of any just simple miscommunication where people read the same spec and interpreted it different ways. So, there's a whole load of internal factors that affect.
The formal spec avoids that situation, is what you're saying, because you have like a way of precisely communicating exactly what you expect.
It reduces it. I mean, it's still going to happen to some extent, but if we can when we can generate bits of simulators from it, you know, measure coverage of test suites, kind of run tests on it, you know, lots of things like that, we tend to catch issues earlier. And having a kind of a good central spec helps with, like, you know, version control and things like that. That web page, people can see instantly what's there.
So you've obviously got quite a lot of experience of doing this with ASL, both at ARM and Intel now. What more general lessons can we learn if we want to do other kinds of big specification, not instruction set architectures, but
Right, so yeah, I guess there's things where you've got something that's going to have multiple implementations, possibly from multiple companies, over decades, lots of people depending on it, so kind of, you know, that sort of situation. It's, I mean, some of it is, again, the kind of, it's going to be hugely costly, so kind of think about how you're going to get as many people on board as possible, how you're going to justify to them the costs involved. Finding multiple uses, you know, most people will want it as documentation. A few people want it for formal uses, some for testing, so, you know, that stuff. I mean, really, what's here, they, you know, use databases as far as you can. You stick things in regular formats as far as you can. Think about how you could generate code of various kinds. You know, I want to measure coverage for my test suite. What would make that easy? I can do that for code, but can I do something better if it's in a regular kind of structured format? Stuff like that. Ben.
So you had this massive spec, and just, you know, releasing a big spec is great, but this sounds more like a living thing where you're constantly changing it and updating it, and just re-releasing it, another 100,000 line spec is not great. So how do you do that sort of piecemeal releasing of updates to the spec? How do you tell people what the updates are and distribute that within Intel to all these people that you don't personally interact with?
Well, so the website, that web page does support diffs, so, you know, and, you know, they will gradually become more useful diffs in time. But, so that's part of it. Part of it is the standard, you know, kind of like, you know, just when a change happens, there is a, you know, a list of changes that were approved for going into that release. So there's, you know, it's, you know, a bit similar to software, you know, do a bit of refactoring, but not so much that people can't see, you know, but that makes the diffs unintelligible, unless you really have to, which case you do. Nathan.
Thanks for the talk, Alastair. So I've spent some time reading specs like these, and sometimes I want the detail that you're talking about, and I think it's absolutely necessary. But oftentimes I want to know, why is it designed like this? And this is a difficult aspect that I think cannot easily be captured by. You sometimes just need to know the history of why it's been built like this. I want to hear any thoughts about how you can transmit that.
Yeah, this is hard. I mean, actually, there's two styles for if you've got a series of increments on your spec. There's kind of two ways you can do it. One is you say, and you can see them if you look at the current ARM and Intel manuals. The ARM manual is, here's the architecture today, and you know, if you're using an older processor, then you can see, you know, not present in version 8.2. Disable, you know, test this flag to see whether it's present. So it's like you kind of subtract things to get back to, you know, the actual processor you have. The Intel manual has gone the opposite way. Each year, some chapters are added to the document, and so you've got kind of this. You know, to find out all the stuff about floating point exceptions, you're looking at about 4 separate chapters and kind of try to kind of combine those. And you maybe kind of want both. I much prefer the monolithic, and that's the style that I'm building. It also means you don't need a language that can describe, you know, kind of aspect-oriented programming or whatever mechanism you'd use to weave in changes across the architecture. The other thing you can do is try to write some properties of like, if you take an exception and return from it, then what properties can you say about kind of like the state you're in? You know, things have been restored exactly as they were, except for something, you know. So, and that was what I was using a model checker for, to try and check some of those properties. But would require kind of like, say, OS experts to kind of say, here's some properties I think hold and that I rely on. Please tell me if you break them by adding a new architecture feature. Yeah.
We have lots of questions and 3 seconds.